And I think it's good time to begin. Hello everyone. Thank you for attending today's session. It's our second one. My name is Mitko Vidanovsky, Product Specialist at the Reality Solutions Group, and I'll be here today to assist our presenter, Seth Koterba, Principal Engineer and High Expert in Laser Scanning and ReCap. The subject for today is Best Practices for Targetless Registration using ReCap Pro. Before I give my place to Seth, I would like to share a few webinar tips and some useful links that you may want to check. Today's session is planned to last for 30 minutes and there will be 10 minutes at the end for Q&A. Also at any time, please feel free to type your questions in the Questions tab on the GoToWebinar app, and we'll do our best to address them all during this live session. If some of them got unanswered, we'll make sure to follow up through email. And also I want to share some of the links that we want you to check them out. Our product page from where you can download the software. If you haven't done so, you may download 30 days trial of ReCap Pro. After the 30 days, everything will remain free except the registration and the survey capabilities. All the latest news, including the webinar schedule from where you can sign in, is being posted to the Reality Computing blog, so realitycomputing.typepad.com. Go there, check our upcoming sessions, and sign in. Our next topic is from photos to 3D models and how to take the best photos for ReCap 360 for photogrammetry. Also, you may find useful content and post topics on our forums. And you can check the latest videos on our ReCap YouTube channel that has many video tutorials. That's on youtube.com/user/Autodesk ReCap. So I think it's time I can give my place to Seth. Seth, if you can hear me, you may begin at any point.
All right. Thanks, Mitko. Thanks for the introduction. Thanks, everybody, for joining. We've got a lot of stuff to cover today, so I'm going to jump right in. So I'm going to be talking about targetless registration, and I'm going to assume that most of the people that are tuning into this webinar are at least familiar with the concept of registration of laser scans. Some of you might be looking to get into laser scanning. Some of you are probably already in laser scanning and using targetless workflows, and some of you may be using target-based workflows. But just as a introduction, I'm going to remind everyone what registration means. We're basically trying to combine multiple scans into a common reference frame. So we have individual scans, individual point clouds from these scans, and we want to bring them into a common coordinate frame so that we essentially have one large cohesive point cloud. Traditionally, this has been assisted by introducing targets into the scene. So you show up in your job site and you go through the environment and you put up a bunch of targets throughout. How do these targets help us? Well, first of all, we need to extract that information from the scan, so we need to know where the individual target locations are at within the scan coordinate frame. And once we have that information, then we can use those positions to help position those scans. And this has traditionally been done in a couple of ways. Initially, a lot of people were doing using survey information, so we go through and the surveyor is going and capturing the location of each of these targets in some reference frame, maybe a building reference frame. And then once we have that information about those individual scans in that reference frame, we can take the individual targets from each scan and snap these scans into that reference frame as you go. A bit more sophisticated approach that's more commonly used today is to use a bundle adjustment of a full target network. So for each scan, we need to find at least 3 targets that are shared amongst the other scans. If you have an inclinometer, you can get by with fewer targets or some other kind of hardware that might help with that. But essentially, we're taking this big network of scans and targets and putting them into a matrix and trying to minimize the error on that. And a lot of times we have weights or constraints that can be used to tweak that, but essentially it requires a lot of experience and training to be able to do this properly. So it's definitely not something for the novice user. So hopefully this gives you kind of a quick, a very brief overview of how target-based registration works. Not a lot of detail there, but we're going to move on to targetless registration here shortly. Just as a point out a couple of limitations of target-based workflows. There's a lot of site prep. You show up in a job site and you got to take your ladder and your target and your duct tapes with you, and you spend hours or days, depending on the size of the project, preparing the site before you can even turn on your laser scanner and get started. Scan placement can be a challenge. In the example that I showed here earlier with an office space, no matter where you are in the office, you can usually see quite a few targets. But how about an environment like this? First of all, it's difficult to find places to put targets, but it's even more difficult to find scan locations where you can see all those targets. So definitely a lot of headaches for field crews in these types of environments. Augmenting the environment, obviously we have to do that, but sometimes that's difficult to do. Imagine like a dirty warehouse like this, you put up your target, and 10 minutes later it's laying on the ground because the duct tape didn't stick to the dirt. There's an aspect of intrusiveness. I've seen a lot of data sets where it's hospitals and nursing homes, and field techs got to go into the kind of personal space of these patients and put up targets around their space. Field techs obviously don't like to have to do that. We have the issue of occlusions and overexposure. So missing targets. You go into a busy environment where you have just enough targets in view, and then as you're collecting the data, someone happens to walk through just at the wrong time and gets in front of that target as the scanner is acquiring that, and you lose that target. With overexposure, there can be times where, depending on the range of the target and the orientation of the target relative to the scanner, you can actually get such a high return that it overexposes the sensor, and you essentially lose that data. So I've seen that type of thing happen. Site revisit is definitely an issue. Let's say you've collected 100 scans and you get back to your office and then you realize that a couple of your scans were bad, or you missed an area of your environment. Now you need to go back out, but you've already taken down your targets, and there's not a nice, easy way to tie in these additional scans back into what you've already done. Accuracy is an issue that it's not often brought up with target-based workflows, but if you really think about what we're asking software to do, to extract the location of these targets, here's what a target actually looks like in a high-resolution scan at 3 meters. Each of these points has a little bit of noise to them, a couple of millimeters depending on the scanner and hardware quality. But we're asking software to go in and try and find precisely where the center of this target is at. And this is at 3 meters, but that target, if you look at it at 5 meters, it looks something like this. At 10 meters, it looks something like this. And now you can see that it's getting much more difficult to try and find a very accurate center of that target at these longer ranges. So definitely need to keep these targets within a certain range for the resolution data that you're working with. All right, so those are some of the things that kind of are limitations of the target-based workflow. Let's talk a little bit about targetless workflow. In the Reality Solutions group, we're big advocates of targetless registration. We've built a cloud-to-cloud-based registration tool in ReCap Pro. Rather than using just a handful of targets within each scan, we're using all the natural geometry, the walls, the floors, ceilings, other objects within the scene, basically anything that we can use to help refine and correct the alignment between these scans. What you're looking at here, for those that aren't familiar with ReCap Pro, this is what the registration screen looks like in ReCap. On the left side here, we have the first scan, which we would call our anchor scan, and then we have additional scans on the right side that we're kind of bringing in and adding into this registration group. The cloud-to-cloud-based registration works by giving the user giving it a hint as how the scans approximately fit together, and then we go in and refine it from there. Those hints are given by clicking on common points between the scans. So we're looking at 2 different scans here, and we would click on something like this, maybe the corner of this ventilation grate. Maybe click on this object down here, maybe the bolt head on this object. But once you've clicked on 3 points between the 2 scans, it gives us enough information to start. It gives us enough of the hint to start the cloud-to-cloud-based registration. On the order of a minute, we have some feedback showing you the results of the registration. And we'll talk a little bit about what these things mean shortly. But that's basically the approach to targetless registration. The ReCap Pro is very simple to use. Obviously, it doesn't require a ton of experience or knowledge. In fact, this one slide is probably enough to get you going and get started on registration. So let's talk a little bit about some of the advantages of this. Obviously, site preparation is much shorter. You don't need to spend forever placing targets in the environment. There's no need to have issues with intrusiveness or dirty environments in terms of augmenting the environment, as we had with the target-based workflows. Moving objects, people moving throughout the scene generally aren't a problem. We'll talk a little bit more about that. ReCap Pro does enable some in-field workflows for being able to do the full registration right in the field. This is great because you can have a fully registered model by the time you leave the site, so you have the confidence that you've got good data, confidence that you've got everything registered, and you've got everything covered that you needed to cover. If for some reason you do need to revisit the site, it's very easy to add additional scans into the data set. No need to worry about targets that might have been missed or something like in the target-based workflow. So a lot of advantages to this. These are a lot of the reasons why we advocate the targetless workflow. Let's talk now a little bit about some of the best practices and things to keep in mind when registering in this targetless process. One of the important things that we want to think about is scan overlap. So in the target-based workflows, the most important thing is to make sure you have enough targets in your field of view. With targetless registration is overlap. You need to make sure you have enough overlap between scans. Geometric constraint is something that we'll talk about. It's important to make sure that you have in that overlap region enough geometry to fully constrain the data. We want to think a little bit about the density and the noise of the data that we have in our overlap region that can impact the quality of our results. We want to watch for large moving objects. As I said before, moving objects generally aren't a problem. In some rare cases, you might have very large portions of your environment that are changing, and I'll talk about that a little bit. We're also going to talk about scanning frequency, or basically the spacing between your scans and the pattern of registration that you may be using. And then last, we're going to talk about some recommended uses for targets. So targets aren't necessarily all bad. We're not saying that you should get rid of targets completely. There are definitely applications where a minimalistic use of them is definitely beneficial. So think about with registration. Here we're looking at a scenario. Let's say it's a top-down view of a couple of rooms separated by a doorway. In the scenario on the right here, the scans are taken basically from the middle of the room, and the overlap area is small compared to the scans on the left side that are taken much closer to the threshold of the the doorway. As that overlap can get very narrow depending on how that threshold. So you want to keep in mind these pinch points, or these narrow thresholds, and how they impact your overlap. So obviously this is better to scan closer to the doorway. In the example that we have here on the left, you could improve that scenario by actually adding a third scan right in that threshold there to get the right amount of overlap. Another thing to consider is the geometry of the environment that you have. So in this scenario, we have a couple of scans that are the same distance apart, but on the left side they're in kind of a large open environment where basically both scans can see everything. So they have lots of overlap between them. On the right side, we're in a much more narrow environment, kind of a hallway corridor, and you can see that the overlap is much smaller. And here this wouldn't be ideal for registration. So keep in mind how the geometry of your environment impacts the overlap. You might need to change up the frequency of your scanning to get more overlap in tighter, narrower environments like this. And this concept of overlap is reflected in the metrics that we're providing as a result for the registration process in ReCap Pro. The overlap number here, basically what this is showing you is a percentage, and it's the percent of the data that you have in the scan that you're bringing in to register, and how much of that data overlaps with the data that's already in the project, so other scans that have already been registered. Okay, so that's overlap. Let's talk about geometric constraint. So looking at this same scenario again, this is a top-down view. The overlap area, the overlap region would contain the floor and the ceiling of this environment. So we would have enough geometric constraint to align the data. This would be, I guess, in and out of the screen in this view. We'd also have constraint up and down in the view. So these walls here would help us constrain the data up and down. But only in the example on the left do we actually have enough information to constrain the data to the left and right of the page. The example with less overlap, you can see that we're just missing the information that's required to fully constrain that data. And this type of scenario can happen as well in very long corridors, so like hallways. If there's an environment where you have a very long hallway where the scan basically isn't able to see enough of the wall at the ends of the hallway, there's nothing really to constrain the data along the length of that dimension of the hallway. So it's you can have this kind of slipping or telescopic effect between the scans. So keep that in mind. There are not many hallways that are long enough where this might be a problem, but keep that type of thing in mind. So this number is reflected in the balance measure, the metric that's returned during registration. Essentially, the balance is going to be high the more constraint that you have. In the example here with the hallway, you're going to have basically a 0 percentage balance because there isn't enough information to constrain the data along that dimension. Okay, so that gives us the balance and overlap. Let's talk a little bit about noise and density. So most of you probably realize that density falls off rapidly with range and when you're laser scanning. Noise also increases with range. Both of these actually change as well with the glancing angle to the surface. So for example, when you're scanning, say the scanner is looking directly down at the floor below it, you get a nice strong return off, a perpendicular return off the floor below the scanner. But as you're measuring that floor out 3 meters, 5 meters, 10 meters, and so on, that glancing and the angle relative to that surface is changing and getting much is changing significantly, and the noise and the density definitely are affected by that. So you get a lot more noise and a lot less density as you get further out. If your overlap region is kind of out in this sparse or noisy area of your overlap, then you're going to have potentially quality issues with the registration. So looking at a density map of a couple of scans, we don't want to have the overlap be out in this very sparse region. You want it to be overlapping much closer within the higher density regions of the scan. So this number is going to be reflected in our quality number here. What this number is showing you is of the points that are in that overlap region, what percentage of them fall within a threshold of the data that's already been added into the registration group. So if your scanning in your overlap area is very sparse, you might see that these numbers start to fall, and so the noise can impact this number. It's not the only thing that can impact this number, but it definitely is one of them to think about. Moving objects, as I said before, moving objects generally aren't a problem, but they can be depending on their size. This data set was actually taken in Times Square in New York City. You can see it's a very busy environment, vehicles, people moving around. And we actually had a good success with registering this data because most of the good geometry being used for the registration are on the walls and the surface of the buildings and the ground. We have some robustness techniques to kind of eliminate some of the motion and noise within the scan. So even this type of busy environment generally works pretty well. But there are examples definitely where you can find places where moving objects can be a problem. Here's one example from that, actually the same data set. This was a temporary structure that was actually being built in the middle of Times Square, and there were some scans collected on the roof of that temporary structure. And the roof was covered in this black tarp. And as people moved around on the roof and as equipment was moved, cables were moved, even the wind blowing, this surface was changing significantly, a couple of centimeters depending on where you were at with it. So it was very kind of a fluid type of surface that was being scanned. And because of that, the quality numbers were impacted, and even the registration itself was not as good as it could be had this been a different type of surface. So keep that in mind. These types of scenarios are pretty rare, but there might be places where you'll find that a large portion of your environment is changing or moving in some way. Okay, so we also want to consider the accuracy of the data. So with cloud-to-cloud based techniques, we kind of have to assume that the data is correct that we're bringing in. So because of that, we want to avoid false geometry that might be introduced. Calibration can be one of the places where this is a problem. When you're scanning with a nice flat, straight surface when the calibration goes, you start to see the kind of waves in the data as the mirrors of the scanner are going to get misaligned. Generally, this isn't a problem. Kind of average out that small amount of noise, but it definitely can impact the quality numbers that you get back. And as it gets larger and calibration gets worse, this can introduce some problems with the registration. Unusual materials can cause a bias for the sensor, for the laser scanner. Black objects tend to give a little bit different return, especially like that black tarp that we were looking at in the previous example. So keep an eye out for some unusual materials. Reflective materials can sometimes be a problem. Usually like a bathroom mirror or a reflective window or something like that isn't a problem. But if you have an environment where a large percentage of the a hall of mirrors or a big glass building or something like that, you may see some issues due to the reflected geometry that's showing up in the data. So keep that kind of stuff in mind. Pay attention for that. Some other things to think about in terms of the registration process itself. Let's say that you're scanning in an office building where you're hopping around through the hallways into office rooms and back and forth. You don't necessarily need to register in the order that you're collecting this data. You can actually go about it in a different way. So one way that you probably would want to do this is to think about your highest overlap scans and try and build a nice backbone of good overlap between scans. And then you could bring in these other scans that might have smaller overlap due to the narrow hallway or doorways, and that might not be as easy to bring in and register. Once you have that backbone, it'll be a lot easier to bring in, and you'll have a much better result. You also want to think about the frequency of your scanning. So you're going to have 3 scans maybe at 5-minute resolutions, or you could do the same type of thing in 15 minutes. You could do 5 scans at 3-minute resolution. Here you're going to have much better overlap between your scans, and you're also going to have a better view of the environment, so fewer occlusions because you'll have more viewpoints of the data. And this is actually really great for things like that very complicated pipe network that we were looking at before. Getting more views and perspectives of the data gets a more full or complete picture of the data that you're in. So think about how you're scanning the data. You might want to make some modifications to that to increase your frequency. All right, so and the last thing I'll mention is related to survey on larger projects using targets. So let's say you have a big project like this, maybe it's a big hospital or a big office building. You may want to think about breaking that up into some smaller pieces. So maybe each of these hallways is a separate project or separate section of the building. Then you can introduce a handful of targets in each of these areas and around the perimeters of those regions, and use survey to bring these pieces in individually. So you can bring these all together, these individual projects together with that survey. So this is sometimes a nice way to break up a bigger project to get better results. Okay, so that's basically it. So again, in summary, we're relying on the natural geometry of the environment, not just a handful of targets. Obviously, think a lot about your overlap and your geometric constraint to get the best result possible. Think about how you're scanning and what your spacing is and how you're registering. And then, think about, for large projects, some minimal use of targets and surveys to help assist with that registration. And that's it. If anybody has any questions, I guess Mitko will be fielding those and passing them my way.
Thank you, Seth. That was great. Before we go into Q&A, I want to ask the audience for one quick question. Question should appear on your screen and you may select any answer. Okay. We have a question coming from Michael, and he's asking, what percentage is acceptable for balance overlap points when registering in ReCap Pro?
Yeah, so I'd say that the most important metric is your quality metric, so how much of your overlap region is aligned well with the data that's already in there. I've seen places where the balance can be really low, but the data that's there is just enough to fully constrain it. I've seen good results with as low as 2% balance before. Obviously, you don't want to rely on doing that a lot, but the better overlap, is good. I'd say at least 30% is where we kind of have the cutoff for the green threshold there. So at least 30% overlap, and you want to be in the mid to high 90s for your quality numbers. And the balance can be a little bit lower, but generally 10 to 15% at least is a good metric to consider.
Okay, and we have one more coming from Marcos. What is the most effective distance between scans? And I would add here maybe what's the most effective distance or resolution when scanning open places, how we deal here, and what should we use?
Yeah, again, it really depends on what resolution of data you're working with. Some people like to work, with a low resolution scan like a Faro. I guess it would be an 8th resolution is probably the low resolution there. In that type of scenario, you probably want to be in the 7 to 8 meter range is probably getting a little bit too far. Right around that area is probably the outer limit of that. You can go higher, quarter resolution, half resolution, and then you can get further range between scans just because you have more data and more overlap. But we generally advocate the more frequent scans on the lower resolution. So in the like 5 to 8 meter range is probably a good example for, or a good metric for how far to be spaced apart.
Okay, we have another one from Marcus asking, do you have some preferences? Which scanner should we use for aligning with ReCap Pro? We are scanning factories. Yeah,
today a lot of the laser scanners are getting to be a lot of the same quality. No real preference over them. They're all pretty good. Definitely, some of the more expensive ones have a little bit smaller noise, but any of them works well.
Okay, thank you, Seth. Thank you, everybody, for joining. We have passed the 30 minutes mark. Thank you for attending. Don't forget to sign up to our next session that is planned for 27th of May, from photos to 3D models and how to take the best photos for ReCap 360. Best practices to get highest resolution models. You may also continue to check our videos at our YouTube channel, and feel free to continue to write us comments and ask questions on recap.community@autodesk.com. Thank you, everybody, and hope you enjoyed, and hope to see you next week. Bye-bye.